Okay, so layout. Okay, this was the problem, huh? So I said that here is Fy. I'm continuing, and this is Fx point O. Here is theta. Here gonna be L sine theta. Here L cosine theta. Hopefully this is recording, yes. Yep. Okay. So, and we have obviously mg. We have obviously here mg. So sum of the moments around the mass center is equal to I mc theta double dot. Here was 0 because the mass moment of inertia on mass center particle is 0. So now, the person that asked me about the sign, now what we're gonna do, we're gonna fix this point at the plane, and I'm gonna apply Fy. Fy in the normal distance, which is L sine theta. Fy L sine theta. Chris, what's the sign of that? It helping the increasing of theta or resisting? Yeah. If you fix the MC point here and then apply this helping, so it's gonna be positive. Chris, you understand? Yes? Chris? Okay. Now Fx, again I'm ground mass center. I'm fixing this point, applying Fx. Gonna be Fx in the normal distance. Gonna be L cosine theta. L cosine theta. So it's gonna be positive or negative? Chris, if I apply Fx, increasing the angle theta or decreasing? Yes, plus is 0. Bingo. Relation number 3. Yes, because I runs on mass center. This is a particle mass. Particle has no dimension, so its mass moment of inertia around its own mass center is 0. Remember when I was teaching you? If you go to I is integration of r square dm. What is the r runs on mass center? 0, because particle has no dimension. Chapter 2, remember the first class? Yes? Okay. So, yeah, go. Oh yeah, yeah. It's a free pendulum. We are releasing from the normal position and coming down. Okay. When you come to the vibration class ME520, we say free vibration. Okay. Then we have forced vibration. Okay, and we go on. I'm not teaching you here because it's not topic of this. Okay. So, and previously we developed together today. Please read those terms for me. Fx was m, what was that? X double dot plus L theta double dot. What was that? Sine and cosine? Read for me. What was here? What's the rest? What is the rest? Guys, nobody wrote this in your notes? No, it has some. This is cosine? Thank you. And here was Fy, minus mg minus m, right, lady? Minus m L theta double dot sine theta. Here was plus, that's right? Cosine theta. Okay, good. Now we're gonna just get rid of Fy and Fx here because I want that you derive the equation of the motion. It's very easy. How? I multiply both sides of this because by L cosine theta, and multiply the both sides of this by L by minus L sine theta, and then add the both. Here we go. Minus L sine theta. Let's do that. The first line. Minus Fx L cosine theta plus the left hand side. Minus Fy L sine theta plus mgl sine theta. This is left hand side. Guys, how much is this, for God's sake? Look at equation 3. How much is that? Exactly, it is 0. Now right hand side. So you're gonna have m, because you have m factored out everywhere. So x double dot L cosine theta, the upper line here. Now here, all of you look at here, don't write. L square theta double dot cosine square, L square theta double dot sine square, because minus and minus is plus. Gonna be how much? L square theta double dot. Here we go. Now minus theta dot square sine cosine and plus theta dot square, so they go to hell. Here we go. We did it. So you can rewrite like this. M L square theta double dot. I'm moving this to other side. Minus mg L sine theta equals to m x double dot L cosine theta. M L with one of this L, and then divide by L. These are from high school. So we're gonna have theta. Oh, you're gonna have. Let me choose a color. Theta double dot minus G over L sine theta equals to x double dot divided by L cosine theta. And bingo, you found the nonlinear differential equation, or equation of the motion of your upper torso when your hip moves. So you're telling me why you teach this? What? What? I cannot hear you. Okay. Okay. So guys, now this was for moving inverted pendulum. Go to your notes. Give me the equation of the motion for moving pendulum from previous class. This is the point I want to make here. Was theta double dot plus G over L, right? Sine theta equals to, what was the right hand side? Great. This is the whole story I want to make. This is was for this, for moving pendulum. Here was moving. Okay, that's take-home message. What I only want to discuss are these two. How many of you passed differential equation before coming to this class? How many of you? All of you passed differential equation? What? Okay. So that's catastrophe that before differential equation come to dynamics. But anyway, so this is not your fault. This is the department fault. So, okay. The name of this is differential equation. When it comes to the vibration control and robotic class, we have to deal with this a lot. Let me tell you this. If the sign of this term is negative, okay, is negative, this means that, as I'm gonna teach you in the upper level courses, your system is unstable. Why? I'm gonna prove it mathematically when you come to the upper level. If this sign is stable, we're gonna name it as in control class ME530 marginally stable system. Marginally stable system. What does it mean? Can I go to next page? Yes. Yep. Yes. The other one is the moving pendulum. Regular moving. This was the moving inverted. This was moving pendulum. Right? See? Okay. So can I go to next page to see what's happening here? Can I? Okay. When I say, guys, if this is negative for inverted moving pendulum, means this, guys. If you release it from here, it's gonna do this ding, 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 ding forever. This is unstable. You cannot control it. Then you have to come to control class ME530 to design a controller to fix it. For example, to keep it at this angle, for example, at 30 degrees. So that negative sign shows that your system is unstable. You have to stabilize it. But when I say this is positive, your system marginally stable, means this. Means if you release from here, it's gonna do this ting 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 ting, gonna oscillate forever. That's why we name in control, we name marginal stable system. It's not unstable, but it's not stable. It's on the border of stability. We say marginal stable system. Sure. Uh-huh. What man, anything that has a changing velocity and has acceleration. Yeah. Okay, that's fine. That's the things that I'm gonna teach you on the vibration class and control class. First, you have to solve these differential equations. Okay? So when you, for example, when you solve this differential equation, your solution angle, okay, after linearization becomes theta of t for the moving pendulum, gonna be, I don't know, a sine omega nt minus phi. Don't ask me what's in n. Omega n is natural frequency in the vibration, but it shows that if this is angle of the pendulum and this is theta, you're gonna have this. So you have theta dot because sine is changing with time. That's right, omega n t, and you have theta double dot. Okay, and none of them are zero. Yeah, yeah. You can give. Okay, good question. You can give. Okay, look at here, Ahmed. This is a control problem. Okay, the input to the system, you are giving that. I say that x of the t must be 0.001 sine 2t. Yeah. Or say x of t when you come to control class is a step function. What's a step function? Is this. Let me show you. This is the function. Here is one. See what I'm saying? And now we apply the function, how this is going to behave. See what I'm saying? Because, but because of the system, Ahmad, is originally is unstable, it doesn't matter that what you apply for the base. The system going to be unstable forever. See what I'm saying? So, yeah, so it's very complicated. I don't want to go further inside because you don't have the skills on that. It kind of makes you confused more than that. Yes, yes, but better example is your torso when you move, okay? And you're gonna tell me, Payman, why I move and that's my torso, why I don't oscillate like this? I mean, I'm not unstable. Because at your hip joints, by the evolution, there is a controller. Okay, I'm gonna teach that in the control class, ME530, how to design it. To make you upright, always, like this, when you move. See what I'm saying? Okay. So let me solve another problem. Problem 644 of the book. And I have the figure of that here. There is a L shape this. And at the end, there is a sphere, solid sphere here. Okay. Problem. Let me go to the book. Let me show you. Problem 644. 644. Okay, here we go. Let me show. If the system is released from rest, means the initial angular velocity is 0, while in the horizontal position shown. Determine the angular acceleration of the lightweight right angle shaft. The sphere of radius r has mass m, negative friction at bearing O. Okay, so look at here. This is the problem statements. Do you see here? We want to calculate the angular acceleration. When we see that, means theta double dot of this right angle L-shaped bar. At the end, there is a hinged mass m, and this is massless. Okay, guys, I have a question. When I say this L-shaped bar is massless, what does it mean? I taught you in the first class. What does it mean when I say this is massless? Can be a bar be massless? Yes. Yes. In comparison with the mass of the sphere, I say is massless. So we are releasing from this horizontal position. I'm going to calculate the angular acceleration of that. So if that 2r, 3r, okay. Here is 2r, and here is 3R. Okay, guys, look at here. What's the which force is acting on the system, guys? One of them is what? Yes. Another is the reaction forces of the bearing area. That's right, point O. Yeah. But we don't care. Do you know why? Because you have to be smart. Point O. Because point O is fixed. Yes. Moments around point O is I respect to point O theta double dot. Here we go. See what I'm saying? Okay. So now, as I taught you in the mass moment of inertia, I'm say here MC, mass center. I of a solid sphere around its own mass center is 2.5. You have your notes. Go and look at mr squared. Radius of that is r. What I'll have to calculate around this axis, O prime. What I have to do? What I have to do? I taught you previously. Parallel axis theory or theorem. I around its point O or O prime is I around its mass center plus m normal distance between two axes. This was 2.5 mr squared. What is the normal distance between two axes? Guys, look at here. How much is that? 3r. That's right? Yes? Okay. So it's gonna be 3r squared. Good. Now you can calculate that. Chris is here. The only moment is mg multiplied by normal distance. What's the normal distance? Yes. Positive or negative, Chris? We want go down. We want this angle goes like this. Mg is, yeah, helping. So it's positive, right? So you're gonna have mg in 3r, obviously positive, equals to only force acting on that is mg. Now this 2.245 mr squared plus 9r squared m theta double dot. If you do the calculations, theta double dot after simplifications becomes 15g divided by 47r. Bingo. Any questions, guys? Simple like that. Yes. If we what? Okay, good. Okay, guys. I'm almost done with this topic. I'm gonna solve problem 647 because I have to catch a flight. I'm going to East Coast for a meeting at 6:20. But next class I'm gonna solve problem 647. I'm done with this topic. and I will go to work on energy principle. Okay? Yep. Go ahead. Do you have any questions? Okay, guys. So let me